Hi guys, welcome to the Speech and Language Technologies Meetup group. Today is November the 12th, Friday. This event is sponsored by OLEDWave Inc. Well, the first paper we'll talk about today is UniSpeech-SAT or SAT, Universal Speech Representation Learning with Speaker-Aware Pre-Training. Oh, by the way, for those of you who are first time here today, feel free to interrupt me if you have any questions, because I wish that we can not only listen to me reading this paper, but also foster a discussion group. I think for those of you who haven't been here last week, I recommend you to check out our YouTube channel. It's you can search the work I've presented, but it's called Big SSL, Big Supervised Learning Technology by Google guys. You can find it, I think, on the OLEDWave YouTube channel. I talk the fundamentals of the latest technology of the SSL. Well, these authors, San Yuan Chen and his colleagues, they are improving this framework for speaker representation learning, and they propose two stuff. The first is the utterance-wise the contrastive loss, and also utterance mixing strategy for data augmentation. So one for loss, one for data augmentation. Okay. For those of you who are not familiar with the Superb benchmark, I would say this is a benchmark which is not ASR based, but it focuses on speaker recognition, emotion, and non-speech recognition benchmarks. This is the task the author is trying to focus. Okay. And the author mentioned that the most pre-training method for speech application focus on the extraction of spoken content information. Remember the wave-to-back or the transformer, they both use the mask, the language model tricks or technique that is being used in BERT, which tries to recover the missing information, which in speech domain, it could be, or it should be the spoken content. But these authors saying, okay, we're interested in seeing whether we can find a representation which is capable of recovering or extracting the utterance level, which is related utterance level embeddings, which is related to the speaker information or non-spoken content information. Okay. Any questions? For those of you who are not familiar with the data set which is being used in speech recognition or speech application, I would recommend you to read the reference from 16 to 18. These are the excellent work by researchers, engineers done recently, and they are selflessly sharing this everything on the shared drive for researchers and to use. Okay. For those of you who are not familiar with Hubert, I'm not quite familiar with Hubert. You can regard. Well, I haven't read the paper, so my understanding might be not accurate, because all that my understanding comes from the background introduction from this work. To me, it seems like it's a weakened wave to back, because the code books obtained from the Hubert is adopting a simpler procedure compared to wave to back 2.0. You can see it just about done a offline clustering on the MFCC feature, so they can use the cluster center of each cluster centers as the codebook centralized. Well, the rest of the training part is the same as BERT, or what do you call that, transformer. Okay, they have these they have the encoder on the bottom, and then they put an encoder on top of it, and then they adopt this transformer architecture. So the loss wise, you can see that they're trying to recover the missing information while the input signal is corrupted. Okay, and what is ZT? ZT is a label, okay, label or the clustered label, okay. They're not calculating the distance. Because they have quantized the MFCC features that they can use labels. What's next?
Sorry, just a quick question. I don't see the screen you're sharing. Are you sharing a screen, or maybe my Zoom is having an issue?
Oh, gee, sorry. I think I'm really sorry about this. Let me share my screen. Well, the thing is, I'm using OBS to record, so I have to share both things. So today I forgot to share. Where's my? Okay, I'm just sharing my desktop. Okay. Can you see me?
I see an infinite number of windows. Okay.
Okay.
Yes. Now I see the paper. Thank you.
Very sorry about that. Thank you for raising that question. So we've done the fundamental introduction of the Hubert. Now I think it's time to introduce the people's work, UniSpeech-SAT. So they developed their work on top of the Hubert model, okay? And first of all, they try to define the contrastive loss. And before that, they have to define their positive instances. So given an utterance, so say utterance of 1 second, and you have 100 frames, right, of MFCC. So, and you get, for 100 MFCCs, you may be able to get 10, 20 embeddings. So all these embeddings are called positive instances regarding this utterance. And the negative instances are called other embeddings from other utterances in the same batch. So this batch has 100 sentences. Utterances. So the embeddings from those 99 utterances are called negative instances. And I have read there, I think they need some more space for doing this. But let me tell you, up to here, from the proposed contrastive loss up to here, this is what is being done at the wave 2 back. This is not new, okay? How the Gumbel softmax is calculated, it's all done in the wave 2 back 2.0. Sorry, when I mentioned wave 2 back, I meant wave 2 back 2.0, okay? And here, is the contrastive loss they are proposing. I think I can go through the math equations, but I don't have a blackboard or whiteboard. So I'm gonna be using their figure to illustrate their concept, okay? So please forgive me if I didn't go into the details of the mathematics. Let's see this. So you can see there are two transformer encoders, right? So the left transformer encoder takes the positive, you calculated the left one is for calculating the positive samples. Sorry, what do you call that? Positive instances. And the right one is designated for calculating the negative instances. So let's see, what does the left part do? So all you can see that, okay, the inputs audio comes in, gets through the CN encoder, and those are masks, right? And pass through the transformer encoders, stack of encoders. I think they should put they should improve their writing. This shouldn't be called encoder. I think they should be called blocks, right? Or conformer blocks or some blocks. And then you get latent representations, L, right? Then L, they went through a quantization procedure, so they get Q, okay? And for a certain time point, you get QT, okay, and LT, QT and LT. So how do they calculate their contrastive loss within these utterance or among these positive instances? So given the QT at time for say 10, okay, they also randomly grab the QT and LT from time 11, 12, or time 5 or 20. So they're throwing this into this equation. Can you see my cursor? They're throwing into this equation, the first part. The sim, they're creating this denotation, the symbol or naming. They should use a cosine distance, right? They're creating this name. All you can see is a normalized cosine distance from two vectors, okay? The kappa is like a smoothing factor or attenuation factor. So you can see, I want to minimize the contrastive loss. So I want to minimize the distance of the QT at the time t versus the representation at I'm sorry, I made a mistake. So they're still trying to minimize the distance between two vectors. Which is the first vector? The first vector would be latent representation at time t of this utterance. And I think this is confusing. The second type vector would be a quantized vector from any time point in this utterance. So this is why they're saying the QT is from the Q. Q means the positive instances, okay, within the utterance. So, and then this is why you can see on the left encoder, the left part. Let me zoom in for you. You can see when they calculate the contrastive loss, the time t, they use a solid line, and for the other time points, time locations, they use the dotted lines, right? The contrast, this is the first contrastive part. Okay, let's see what's the second part. The second part is similar. all the difference is that this time the latent representation LT is the same. LT is the same. But this time, the QT, where the QT come from? They're coming from all the negative instances, which are from the utterances in this batch, other than these utterances. Okay? And you can see similar thing. I don't want to repeat it again. But let me do that for you so you can understand better. So the latent representation is coming to the loss calculation. And then you also use the other QT from the other utterances and send into the loss. And this time, you can see my cursor here. This second part of the equation, they also want to minimize this. So they want to maximize the distance between these two vectors. I hope you're with me, okay? The distance between these two vectors. So they want the LT to be away from the QT, from other utterances. So why do you want it? So why do you want this? I give you 10 seconds to think about this. Well, the reason, my understanding is that different than the traditional or the previous spoken content-based contrastive loss or losses, they are all calculating within this utterance. Okay, all the thing they're trying to learn is to minimize the latent repetition of L to the Q or something like this. They're trying to predict exactly the Q. But this time they're saying this. They're making this assumption. So within a batch, so they say there are 100 utterances. So they can, because they have so many speakers, so many utterances, they can safely assume that all the utterances are from different speakers. So you can see that. When they're saying this, I want to minimize the distance of the vectors or representations within these utterances. They want to see if they can get a homogeneous representation of a speaker within the utterance or the speaker, okay? And they wanted this representation to be away from the other speakers, aka the other utterances. So this is characterized in the second part. They wanted the distance or the representation from this speaker to be away from the representation from other speakers. Okay, so you can see they're doing this in the utterance level, but they're trying to get a representation which can discriminate representation from different speakers. But the thing is, they haven't developed the representation on an utterance level. They're still doing this on a frame level. So this thing looks a little bit, odd, but I think their experimental results shows that this works. Questions? Okay. I think the utterance mixing part is their second contribution, but I think that this one is fairly straightforward for you to understand. So all they do is, okay, so remember on the left one is for the positive, or this is the target speaker or the main speaker, okay, or the utterance. And what they do is that they randomly pull out some other utterances or noise from the training set, and they overlap the interruptive recording with the target recording. So you can see these two recordings are mixed, probably at different SNR, probably at different intervals. So this way, they're introducing some disturbance. They're making the training more difficult to learn. So I think the goal is trying to make the representation more robust to the adversarial scenario, which the noise is presented, two speakers are talking at the same time, they can still have a robust representation. I think they have to improve their writing. I think it's very difficult to understand. Implementation. Well, I think different than the Libre Lite, which is 60K hour of English speech. They use another data set. But I think the data set is available to all of us because they use the latest Giga speech and some other YouTube data, something like this. So this data is, has a bigger size compared to the Libre Lite, which is 60K. This one has almost 100K hours. So I would say this is not an exact fair comparison between these methods. Well, the author knows that, okay? But the thing is, you can see, so whenever these guys are using a reference number after the name, that means he didn't run the experiment, okay? He just copied the numbers that are published in these papers and over here. So this is why I'm saying you can see, the author knows this. You can see the corpus part. You can see they're using different corpus, right? So I don't think this is exact apple-to-apple comparison. But it definitely shows that, you know, with more data you can get better results. And especially you can see the work from itself. This is the base model. You can see when they add the contrastive loss, it's a little bit strange that it first drops off. I think this is not good results because it seems that the proposed method didn't work as well as the baseline. Did you get it? Because the smaller the number is, the better the performance is. For speaker tasks, I think this is for speaker verification. And this is for content. I forgot what the content is. I really don't know these tasks, but see, for this task, this is working. See? No, I don't think so. I think for the content, this is also not working. My guess could be, you can see this is not working for the Libre Speech 1,000 hours. My guess is probably the data is not that much. So this is why when they move up to 90K hours, the result becomes much better than the fewer amount of data results. But you know, everybody, including me, may have this question for the authors. Can you compare or do ablation study on the UniSpeech-SAT base plus, so we can see how it works on the large amount of data? Okay. Here they're talking about when they mixing the speech with the target speaker, what's the mixing ratio it should be. They're saying that if you mix it too much, the result might get worse. But you want to mix at a certain type of ratio, which is good. Okay, I'm gonna stop here. Any questions? Let's see the chat channel. but I think this is a generally um, very novel contempt or trying um, on the direction of learning a speaker based or speaker aware representation other than the spoken content based representation. Although I mean the result is not, I mean to me it's not that proper, to demonstrate their proposal. But I think this is a very interesting uh, attempt in this domain.